Good afternoon, all of you. So welcome to the final session of the day. And today is the third and the final Infosys-ICTS Chandrasekhar lecture by Professor Anna Maria Ray. And today's topic seems very interesting, which also involves music. So it's SPD BEC, easy as 1, 2, 3, music, pairing games in a cavity. So over to Professor Anna Maria Ray.
Thank you. Thank you so much for the introduction. It's really a pleasure to be here and give my third lecture. I know that we all are tired and it has been a long day, so I would like to have this lecture as relaxing as possible. And with that purpose in mind, I think we are going, hopefully we have fun when we start to think about pairing games in a cavity. You can see there are letters here. There is music, so I imagine doesn't anything make sense to you at the moment, but hopefully as the talk goes on, makes sense. And you will have a test about music recognition later in the talk, but I think the whole idea here is trying to convey that these systems, atoms loaded in optical cavities, can be a powerful tool for quantum simulation as well. So yes, remind you again of the scientific vision of my group and maybe all of us here, that is we wanted to bridge the gap between the behavior of few to very many body systems by taking advantage of the control microscopic tunable interactions and access to quantum dynamics that ultracold atomic, molecular, and ionic systems offer towards application in advanced materials for quantum simulation, quantum computation, quantum sensing, and hopefully with that advancing fundamental physics. And as we discussed yesterday, I presented a few of the challenges that we need to overcome to accomplish these very exciting goals. And well, today I'm going to focus on the challenge of trying to cool these atoms in the sense that, well, we know that we have fully controllable quantum systems and we have been able to control the motional degrees of freedom of these atoms and reach conditions where Bose and Fermi statistics start to manifest. And we have heard many exciting talks today about that. And the possibility to further control the interactions by loading the atoms in Fermi hover models that emulate phenomena of a condensed matter system. That sounds very exciting. As I mentioned also yesterday, the issue, however, is that when we have atoms interacting by contact interactions, then in order to see, for example, magnetic phenomena in these systems, when two atoms are separated at different lattice sites, an atom to see the neighbors and understand and check or try to see how it has to align in order to minimize the energy depending of his neighbors. It has to tunnel, see the spin of the neighbor atoms and tunnel back. So magnetism, manifestation of magnetism is really closely connected or linked with motion. And this is what has made the cooling of these systems very hard. On the other hand, systems where the magnetism can manifest even in conditions where the motion is irrelevant because they are decoupled, it opens future or more exciting opportunities in order to explore rich many-body physics and magnetism even with frozen atoms, frozen arrays. And as again, because a spin can be cooled very well, and because motion is not relevant in this case, then we can open the possibility to explore a new type of phases that are associated with magnetism and systems that satisfy the possibility to have or that can have a decoupled spin and motions are those that interact at a distance, like polar molecules, magnetic atoms using via dipole-dipole interactions, also Rydberg atoms, but we have these cases of atoms in optical cavities and trap ions that interact via photon or phonon-mediated interactions where the interactions are really of infinite range. And the idea is that maybe then we can try to go back and when we understand the magnetic phases in frozen atoms, we can shed light on some behavior of quantum statistics. And today we are going to tell you that actually even frozen atoms, without letting the atoms to move, can be used to simulate phenomena that require spin motion in cold atom systems interacted by contact interactions. So again, so our protagonist of the talk is atoms in optical cavities. And I'm going to address, as I mentioned, the challenge of cooling and trying to instead use synthetic matter encoded in the spin degrees of freedom, taking advantage of the long range or infinite range connectivity that atoms in optical cavities. So yesterday I tell you about all these other directions, but today the focus is going to be more on the cooling challenge and how we can use these systems for exploring quantum simulation in very new landscapes. Okay, again, I'm not the experimentalist. I mean, the experiment has been done in the group of James Thompson in the cavity QED experiments. This is a picture of the amazing students, postdocs that really took the data. In particular, Dylan Jung and Jung Koo are the ones that made all this work possible. They work very closely together in this topic. And they were previous experiments by Joseph Taiwasen, where we were trying to start exploring minimal instance of this type of physics. Okay, as I was mentioning, pairing games is going to be the main topic of this lecture. And for that, when we think about pairing, of course, a holy grail is the idea of fermionic superfluids on superconductors, or the exciting idea, fascinating idea that at ultra-cold temperatures, fermions experiencing attractive interactions can minimize the energy by forming Cooper pairs in one conditions or very time-bound molecules. And all these very interesting physics, in fact, can be described by a very simple model that was derived already many years ago and led to the Nobel Prize in physics, which explain this type of pairing in systems of electrons where the attractions between them can happen by the deformation of the lattice in which the electrons move. So even though Coulomb interactions are repulsive between electrons, still they can attract via the deformation of the photons in the ion crystal, in the ionic lattice, and with that we can reduce the energy by via forming Cooper pairs and pairing in these conditions. So the BCS model actually is able to reproduce and account for this physics in very simple terms. So what the BCS model has is two main terms: the kinetic energy of the fermions. Here K is the momentum, C is the field operator that destroy a fermion in momentum K, and sigma is the spin. We can thinking about the spin up and down electrons. And then in order to simplify the interactions, it assumes that the leading type of processes that generate this attraction after eliminating the photons can be written in terms of this Hamiltonian. It looks a little bit more complicated, but basically this term is saying that there is an interaction pair that destroy a fermion in momentum K and Q, in momentum minus K and K in different spins, and then create a Cooper pair also in opposite momentum, Q and minus Q with opposite spins. So basically, this type of idea is going to favor the formation of Cooper pairs or attractive particles, and actually the wave function that minimizes this type of interactions is a superposition between a Cooper pair or an eddy-side. So this very simple trivial answer of superposition then is what minimizes this term. So, but in this Hamiltonian, I also have added a form factor here, F, and I have other that has labels Q, K, and L. So I'm going to explain in detail what this means. L is going to be the pairing channel, and Q is going to be the dependence of the pairing channel on the momentum of the colliding particles. So basically what happens, if you look at the energy of the system, because of the Fermi statistics, what you are going to have is that all the levels are going to be populated up to a Fermi level that can be at 0 temperature, exactly correspond to the chemical potential of the system, and then all the other states are going to be empty. But in the presence of these attractive interactions, then the energy is minimized by generating these coherent superpositions between double occupied sites, Cooper pairs, and empty sites, and this is at the heart of the BCS wave function. Okay, the degree of pairing is characterized by a simple mean field approach where we have the pairing function or pairing gap or order parameter that is proportional to the expectation value of this CC operator that actually kind of encompass the strength of this coherence in this superposition. So basically, this is a system where have a finite order parameter, then we say that there is pairing in this channel L. Okay, so a little bit more of this pairing form factor. The important part is that, again, we are going to characterize this L or the possibility of pairing into the different quantized angular momentum channels. N equal to 0 correspond to S wave channel is a pairing where is spherically symmetric, is the lowest possible symmetry that we can have in our system of pairing and is the most standard. But there are other type of pairings that are L equal to 1 and L equal to 2, for example, that are known as P plus IP and this D plus ID. And what is characterizing is the pairing happens with angular momentum that is finite. So in N equal to 1, you have pairing with with 1 unit of angular momentum, and you can see that the non-trivial topology character of the state can be seen by the fact that as you go around in momentum, you can see that there is a change in angular dependence that gains a phase of 2 pi's or a 1 unit of circulation as you go around and go back to an initial point. Whereas when you have L equal to 2, you can see that there is a 2 units of angular momentum, and then here you have a phase winding that is order 4 pi instead of pi when you run around. And the channel is characterized by a magnitude of the momentum of the Cooper pairs and a phase that is once here and is twice of the frequency. So this, well, it's a little bit complicated, and when you see the Hamiltonian looks hard to understand, but actually something that has been very useful for me is the Anderson pseudo-spin mapping that was proposed by Phil Anderson that reduces the BCS Hamiltonian to a much simpler model that I understand much easier. So he says, well, if you are going to describe the ground state of a superconductor, clearly the only or the relevant states are states where you have a Cooper pair or an empty site, because states that have a single electron in pair cause a lot of energy, so we don't include them in our system. So then in this case, we can associate a Cooper pair with a spin up at momentum K, and a Cooper pair and an empty site or a hole at this K minus K with a down spin at site K. So basically, this is very simple mapping, and then we can understand the state of for a given K. We can see that, I mean, if it's occupied, the spin points out, it's empty, point down, and any superposition, that is when there is pairing or non-zero order parameter, is when you have superposition in the equator. That is going to be this yellow region here. So, moreover, we can rewrite the fermionic operators in terms of very familiar spin angular momentum. So this term that destroy a Cooper pairs is very simple because it's an S minus operator that brings up to down. And in the number of Cooper pairs can be related with an operator that is C, that if there is a Cooper pair, you have plus 1/2, and there is not a Cooper pair, you have minus 1/2. So, and I mean, there is, of course, there is then a corresponding connection between SC and the number of Cooper pairs. This is just what I said before. So now, then the Hamiltonian can be rewritten in a much simpler way. We have the kinetic energy is going to be rewritten as a inhomogeneous axial field that, I mean, with K is just the kinetic energy measured respect to the chemical potential. And then the term that is the interactions is just an exchange model, S plus S minus, and summing over all K, Q, and all different spins. Okay, in that picture also, the order parameter is just the coherences of the system, that is just the sum of S minus of spin operators, expectation value over all K, weighted by the form factor of the corresponding channel. So, well, this is one aspect of the pairing. The other pairing is that of the aspect of the pairing is the form of the pairs. So as I mentioned before, it can be weakly bound Cooper pairs or can be instead tightly bound molecules. So in the case of S-wave, this is characterized by what is called BCS, BEC crossover. It's a crossover for the kinds of S-wave, and going from when the chemical potential is larger than 0, we have just a state that is composed of very weakly bound Cooper pairs. And on the other hand, when we go to and we increase the interaction strength, the chemical potential becomes negative. And in this case, the ground state is characterized by tightly bound molecules. What if you look at the distribution of as a function of K in the BECS regime, so you can see that the state with K equal to 0 is occupied. And then as you go to the BEC regime, there is a change of behavior, but there is not a very abrupt change of behavior. So it's just, you can see just a decrease of the occupations at K equal to 0. Just to say that, I mean, this BEC-BCS crossover is not something that is only interest of condensed matter and ultracold atoms, so goes beyond that. For example, it's believed that at the beginning of the universe, actually the quark gluon plasma and the physics at this early stage was characterized first by hadrons that are the equivalents of the molecules and that are competing with the Cooper pairs that in this case are of the form of where the gluons are a little bit of the confined, and then you have instead of Cooper pairs the analogs of Cooper pair in the system. So just saying that it can be beyond just the interest of ultracold atoms. So moreover, all this story is about the static properties. But of course, condensed matter physicists were also interested in understanding what happens if you do quenches, especially theories. And there were investigations of what could be the dynamical phases of quench superconductors. So basically, they started to ask the question, how the order parameter changes if I do a very fast change of the gap function from one value to another? How is the order parameter going to evolve? And the theories actually came up using this BCS model that is in some sense a very simplified model. They came up with almost analytic solutions of the type of phases that the systems can acquire, and they found that there are 3 types of dynamical phases. They call phase 1 when the order parameter decays very quickly as a function of time. They call phase 2 the case where the order parameter starts to feature transient oscillations until they saturate a finite value, so the order parameter remains finite. And they said that there could be another phase that is called phase 3, where the order parameter keep oscillating indefinitely. This was connected with the idea of time crystal by Wilczek is our Floquet superconductor. Okay, this was interesting predictions, but nevertheless, in solid state materials, these type of quenches are not easy to do. And even though there has been a lot of efforts and especially progress when they were able to use terahertz probes that were not fully destructive, still the evidence of phase 2 is not completely clear. I mean, there are some controversy, And well, it was done not only in traditional superconductors, but even in high temperature superconductors. And furthermore, in this phase 3 has never been observed in these systems. Now, what became very exciting is when we started to produce gases of Fermi gases at ultra-cold temperatures. And I mean, I cannot miss a opportunity to acknowledge the Beijing, who taught us how to cool these gases. And this is a picture with Cindy and Marcus Greiner, where they were able, in fact, to show that ultra-cold Fermi gases can feature this BEC-BCS crossover as I change the magnetic field that controls the strength of the interactions. So in some regime, we can have very tightly bound molecules, and in the other regime, you can have Cooper pairs separated by a point where the scattering length diverges at the unitarity point. So, I mean, they show us that it's possible to see this type of phases, and in fact, this unitarity region is what it was connecting to what I mentioned before with a quark gluon plasma at the beginning of the universe, and even more exotic behavior in superconductors, in materials. But something that has been always a challenge in these systems is that background collisions are detrimental in cooling the fermions, because only one fermion that disappears at the bottom of the trap is enough to raise the entropy significantly. And second, rapid quenches of the magnetic field has been very hard in these systems, and therefore these dynamical phases, even though proposed, have not been seen. So now is the proposal on how we are going to be able to see this type of phases and phenomena using atoms in optical cavities. So the basic idea is that, for example, in the case of strontium atoms, we can use two optical states or an optical transition. The one is 0, the ground state, and even though we can use the clock transition, sometimes this is a little bit too slow to see the physics that we want, but we can see another transition that is still very narrow, the 3p1, that has a line width of 7.5 kilohertz. It still can be 3 or more orders of magnitude slower than dipole allowed transition, which is great. So what we're going to do is that we're going to put well, of course, there is cavity loss that we cannot ignore, but the important part is when we put atoms in this optical cavity, I'm assuming a single relevant cavity mode. The Hamiltonian that describes the atom light coupling is super simple. Here A is the operator that destroys or annihilates a photon in the cavity. Delta C is the detuning between the cavity mode, the frequency of the cavity, and the atomic transition. G is the single atom Rabi coupling that tells me the rate at which atoms exchange photons. In the system, I can see that I define the collective S- operator is because no matter where the atoms in the array, they can exchange photons. So I can define not an individual spin, but a collective spin where I'm summing over all atoms. So that means this is the very nice aspects of optical cavities. And the important point is that in many situations, as I discussed yesterday, we don't want necessarily to deal with the photons directly, because unfortunately they are a little bit lossy in cavities, but we want to adiabatically eliminate it and use them as a mediators of the interactions. So if we operate in the regime where the detuning is much larger than any other parameters in the system, then what happens is that the cavity field is going to follow what the spins does. So I can, what we call, adiabatically eliminate the photons, and their behavior is going to be completely a slave to the behavior of the collective spin. This is going to be super important. Now, if we replace this ansatz of A being a slave to S in the Hamiltonian, you can see that the effective Hamiltonian that I get is a Hamiltonian that is chi S plus S minus. So basically, this process is telling me that I have an atom in the excited state, an atom in the ground state. The atom emits a photon, and because the detuning is so large, before it leaks out and escape from the cavity, is absorbed by the other atom, and the atom can be anywhere in the array. So the effective Hamiltonian is a collective S plus S minus interaction where I sum over all possible exchange in the system. And well, as I mentioned yesterday, these terms can also be rewritten as s squared minus sc squared. That can have very interesting implications. But for this case, for this talk, I'm going to remain grading these interactions as chi s plus s minus. And chi is determined by, if it's basically g squared divided by delta in the regime where delta is much larger than any other parameter in the system. And of course, this type of interaction has also explored in many other groups around the world. So now, if we look at the cavity, the Hamiltonian that we can engineer in the cavity, so we have the S plus S minus interactions that occur naturally in the system. This, as I mentioned, is the phonon-mediated interactions. And if we want to recreate the BCS model, the only thing that I need to do is to re-engineer a single particle term. That's the only thing that I have to implement. So basically what I'm doing here is that I'm replacing the momentum label in the electrons, in the superconductors, by a position label, because I can generate some inhomogeneous energies of the atoms that depends on where they are in the cavity. So moreover, what is important to also remind ourselves is that if I wanted to simulate some type of Fermi statistics, what happens is that we are going to have states that are occupied below the Fermi surface, the Fermi level, empty above the Fermi level because it costs energy, and in the middle is where we have this canting that is introduced by the interactions. So we don't have Fermi statistics, but what we can try to engineer this type of energetics in our system by actually introducing a star shift only partially on one part of the cloud. So if there is a star shift on partially one part of the cloud, then I can recreate the situation where, for example, these atoms are going to point down, for example, because I'm going to generate a dispersion relation that is going to be, that can be linear, and in this case, and can be negative when the cloud is illuminated, and can be effectively positive in the other region. So in that sense, I am artificially engineering a type of Fermi statistics in my system energetically. And I do this, as I said, by introducing AC star shifts, and moreover, because there is light leaking out of the cavity. And then, as I mentioned, the field operator is proportional to S minus. By measuring the intensity of the atoms, of the photons that are leaking out, I can access directly to the order parameter. So this is a very interesting opportunity because it's super hard to measure the order parameter in condensed matter systems, even in ultracold fermionic atoms. But here, just by tracking the intensity of the light that goes away the cavity, I have direct access to the order parameter. So in fact, we were able to implement these three and observe all these three dynamical phases for the first time that were predicted to exist in BCS superconductors. So what we did in the experiment is that first we tried to observe the transition between phase 1 and phase 2. And the idea is that we first apply a pi-half pulse where we create a lot of coherence between the excited states. So the order parameter was maximum in that sense. And what we did is that we look at the response of the coherence of the systems, of the magnitude of S minus, as a function of time, as we change the number of particles in the system. So in one case, we operated with very small number of particles, and we increased the number of particles, changing the value of chi-n. So when chi-n was super small, the order parameter very quickly disappeared. No coherence, because there is not, as I was mentioning before, there is not a protection, there is not S plus S minus, or everything decay. But as I started increase the strength of chi-n, you can see that the coherence are protected and increased. This is the ideal theory for the maximum value of chi-n that we use. So in the theory, there is no decay at all. The decay in the experiment is unfortunate because we do have single particle decoherence, finite light scattering that makes the process not ideal, but still we have been able to increase the coherence significant by increasing the value of Cayenne. So basically, we started quenching the system by going to a point where the order parameter was maximum, and then going in the border between phase 2, where there is a finite order parameter, to all the way to phase 1. But also, we were able to do quenches by changing, now playing with the bimodal distribution introduced by the star shifts, and we were able to do quenches between phase 2 and phase 3. Basically, in phase 2, it's very similar behavior as we had before. We apply a pi-half pulse and let the system evolve, and as we increase the energy splitting between the two parts of the cloud, we can see that the system starts to have periodic oscillations. These oscillations are not infinite, they don't last forever, but if the behavior is very consistent with, the solid lines are theory simulations, these other lines, more intense lines, are the experiment. So we were agreeing with the behavior expected as we quench the system. So this was a manifestation of seeing the phase 1, 2, 1, 2, and 2, 3 in our system. A little bit very quick comments, and maybe just mention that we do see, and we could enhance the transient oscillations that are called as Higgs oscillations. We were able to increase them and try to play with them, but yesterday I showed you that we have also graph protection in our rubidium system, and in this case perhaps the Higgs oscillations are a little bit more pronounced. You can see these very nice wiggles when we increase the value of Cayenne compared to the fast decay where there is no chi. So these behaviors are completely related to the physics that I showed you yesterday. Let me say that very recently, there was a Fermi-generated gas experiment where placed themselves a unitarity, and were able also to observe for the first time some type of Higgs oscillations, but the tunability was very limited, although they do see very nice similar type of physics that we see in our artificial BCS superconductor. Okay, so maybe this system is super trivial, but on the other hand, it allows to answer some of the questions that cause a bit of confusion in the past, because when the possibility of create a BCS superfluid was proposed, one of the first questions is how we are going to probe that there is superconductivity or there's superfluidity in the system. So as usual, very important work by Peter Soller shed light on how to do it. Peter said, okay, let's use a third state, and we do RF spectroscopy if we have pairing between state 1 and 2, two different internal levels of the atom. If we try to do a transfer of excitations between 2 and 3, then the cost that I have to do compared to non-interacting atoms is going to measure, trying to measure the gap, superconducting gap. Where later, and this is, I'm quoting a review of Wolfram Ketterle, they actually became aware that while this provides information of the presence of superfluidity, was not necessarily measuring the order parameter of the superconductor, and the frequency that they need to actually break the pair was more associated with a measurement of the spectral gap. So what I'm saying is that this is going, the superconducting order parameter and the spectral gap that we're measuring in those type of experiments was not the same. And it was super confusing. So the question that we were trying to address is that if we can see and clarify this question in our simplified model. And in fact, we could do that because what we can do is that, in fact, we have 1 is 0, but the triple one not only have two, we can have up to 3 levels. Basically, in our system, we removed the 0 state that we can do, and we were using a superposition between -1 plus 1 as a bright state, that the state that directly couples to the cavity, but there was a state that is the dark state, that is the antisymmetric superposition that doesn't couple to the cavity. But furthermore, we can add a Zeeman shift, and the Zeeman shift splits the energy difference between the plus and the -1. And the idea is that if we write our model in terms of these bright and dark states, that are the antisymmetric superposition that doesn't couple to the cavity, and the symmetric superposition that does couple. In this case, the magnetic Zeeman shift is just transferring, is a transfer between the bright to the dark state and vice versa. So this was exactly what we were doing in the spectroscopic that they did in the past, because in this case, my dark state acts as a third state. And in fact, so we were able to perform this experiment again, and we were trying to understand now dynamically what happens when we are going to try to transfer. There is a finite Zeeman shift that is going to couple the bright to the dark state. And in addition, there is cavity-mediated interaction between the ground and the bright state. And we were trying to measure the dynamical oscillations, like some type of Rabi spectroscopy, when we performed this protocol. And I mean, there are just various equations, but what we were able to derive very simple is that while the spectroscopic gap depends on the number of particles in the ground state, the order parameter is not. It depends on the coherences between the ground and the excited state. And in fact, we were doing different experiments where we were able to actually measure the frequency of the oscillations and the spectroscopic gap, and as a function of the magnetic field, and we were able to show the difference between the superconducting gap and the BCS gap by changing the initial typical angle of the state. So basically, the coherences, that is going to be the BCS order parameter, is going to be maximum at when you have pi half, because it's the maximum coherences, whereas the spectral gap, on the other hand, is going to be maximum when we have large population of the ground state. So this is just to show that even though this is super simple, it can shed light to a lot of confusions that well, it was resolved, of course, before, but it can shed some light on that. All right. So, okay, so now I hopefully you are going to identify this one. I don't know if you do. It's Michael Jackson. It's ABC. So at the moment, you might have already identified 1, 2, 3. You have identified BC. You have identified S. And now I'm going to tell you more about the PB, that are going to be the topological non-trivial phases. And I'm going to tell you our proposal of how to engineer them in optical cavities. So the exciting part of this higher momentum, finite angular momentum pairing is that these are not conventional superconductors, but they lie into or correspond to the type of what is called topological superfluids, especially what they are preparing in 2 dimensions. So the interesting part is that when you look at, now you remember the Anderson said the spin mapping, that for a given momentum can associate a specific spin, down if it's empty, up if it's occupied, and in the equator if there is some coherent superposition, maximum. What you can see is that if you are trying to look at the textures of the BCS, BEC, you can see that always, because at the edges, there is no spin, there is no, I mean, everything is empty. The states that have high energy and momentum are empty. If the spin at the center is also empty, is down, there is no topology. So the BEC has no topology and the spin at the center is always down. Whereas when you go to the P-wave BCS and the D-wave BCS, on the contrary, you can see that the spin at the center is always up, and moreover, there is a winding number of 1 and winding number of 2 in the 2 different phases. So this is very exciting because actually these 2 states are topological, and therefore going from here to here, instead of being a crossover, there is actual a transition. There is a topological phase transition in the system that has not been seen yet. There has been a lot of effort and also many candidates in condensed matter systems, but so far these phases have remained elusive. So now a little bit of correction. Remember that I told you before that the BEC and the distribution of Cooper pairs in the BEC, BCS and the BEC is different, but not so drastically different. What characterizes the transition between the BCS and the BEC is that actually at the At the BEC phase, in a topological superconductor, the occupation of the k equal to 0 mode is always 0. And this happens drastically, very abruptly, non-analytically. And this is another way to encompass the characteristic of the phase transition. So if you define a winding number, you can see that the winding number, in fact, is associated with the value of the chemical potential. If the chemical potential is larger than 0, then this Q can be 1 or 2, but if this chemical potential mu is negative, then this Q winding number is 0. But moreover, the chemical potential is exactly associated with or this value is associated with the orientation of the spin at the center. Here. So what is our proposal to realize it in an optical cavity? So what we have to do is that we have to drive the atoms with a drive along the cavity direction, but we need another drive perpendicular to the cavity direction. And if we want full glory of the system, we wanted to also add not only a 1D, but a 2D lattice where the atoms are trapped. So there is a 2D lattice inside the cavity, and we're going to drive the cavity parallel and perpendicular. What is the idea? That when we drive the cavity, because it's a standing wave cavity, when we drive along the cavity direction, there is a cosinusoidal dependence because the light bounces back and forth, and therefore it constructively interferes, and the light cavity mode has a cosinusoidal dependence, and this is shown here, that doesn't have to be necessarily commensurate, that's key, with the periodic structure of the lattice. So when you have two drive illuminating the atoms, first, what you can do is that you can generate AC star shifts because an atom absorbs and emits back, and this is the standard star shift. That's how we create the periodic potential. So one star shift is homogeneous when we have the laser that is just the other part is that the laser that is perpendicular to the cavity is going to be just not a standing wave, but just propagating along one direction. So it's in this case, the star shift is uniform, but on the other hand, the star shift that is important generated by the other drive is going to have a dependence that is cosinusoidal as well. And finally, if we are going to include the photons inside the optical cavity, we are driving one mode. What happens is that an atom can absorb, and we're going to use very different frequencies, so they're not going to interfere. But if we have an atom, two atoms, for example, in the ground state, I can have a process when one atom absorbs a photon from the drive and emit the photon, the cavity photon. And another process when I absorb from the other drive and emit a cavity photon. So what happens is that an atom can go from down to up and therefore flip the spin by generating a cavity photon and absorbing photons from either for the first drive and for the second drive. Yes, and the idea is that if I'm going to consider the regime where the photon is far detuned, as always wanted, because I don't want them to be active, I can adiabatically eliminate the photons, and therefore I can generate an exchange interactions that can have different forms. Here, eta is the cosinusoidal character of the state. So in one case, there is always a four photon process. I absorb from the drive A, emit a photon, absorb a photon, and go back from the drive A. So I have two cosinusoidal cases if I associated with this photon for one case, but when I have the photon also from the cavity, I have four cosinusoidal terms. And this is the idea how we're going to emulate the superconductor. The idea is that, remember that I told you that the form factor of a P plus IP superconductor have the form of K plus AY or KY of the norm of K time of phase. So in our mapping, what is going to happen is that we are going to unravel the KY and K explained in some form that the radius, the surface that are at fixed radius are going to be surface at fixed X, because at this point all these points have the same coupling to the cavity. And on the other hand, we are going to assume map the points at fixed angle by the orientation, by the position along y, because the laser that propagates perpendicular to the cavity then is going to be implying a phase that just changes as we move along y. So in that way, we are going to unravel the P plus a P structure of the superconductor, and then this Hamiltonian that I'm writing before emulates the form factor that I have for a P plus IP, and this term emulates the form factor that I have for a D plus ID. So this is, imagine that this is K squared, and this Kx squared, Q squared, and then the corresponding phases, and Kq and the corresponding phases. So we are able to generate these two forms of P plus IP superconductors. Furthermore, the photons that are leaking out of the cavity have information of both the order parameter associated with the P and the order parameter associated with the D, because the drives that generate the P and the D have different frequencies and therefore different detunings of the emitted photon with respect to the cavity mode. So by detecting the photons that are leaking out of the cavity, we can measure two order parameters by doing just an heterodyne detection. So we can access both of them. So, I mean, you can do always a mean field treatment. That's the beauty of these models, that you don't need to do very complicated physics. But for example, the ground state using a mean field treatment is going to be associated with the orientation of the spins that are depending of the self-generated field, that we have a C component from the kinetic energy, but also have a transverse component because of the pairing. So that's the idea. Now, in order to create the phases, you are going to say, well, the problem of P plus IP superconductors is that the temperature conditions are very hard to reach. And this is the case for fermionic gases. In our case, it's super easy, because what I have to do is just only to drive my system. So basically, if I also add a classical drive, then I can have real Raman transitions that are going to determine a very simple magnetic field that is the C component is going to be depending of the detuning of the two Raman drives, and the order parameters are going to be associated with the strengths of the two Raman drives. And I just need to map the value of the detuning to the chemical potential and the transfer components to the order parameters, and with that, I'm creating a ground state superconductor. And moreover, if then I let the system evolve in a way that the actual order parameter that I get when I remove the classical drive and I use the photons in the cavity, then I can do quenches. So basically, I can explore the phase, again, the dynamical phase diagram, but in this case for P plus IP phases, and you can see that I can get the phase 2, phase 3, or phase 1 in this system that is now topological non-trivial. Moreover, I can measure the non-trivial topological phase transition in a very simple way. I just need to look at the phase of the photons that are leaking out of the cavity, because what happens is that the order parameter is going to have a chemical potential, and depending on the sign of the chemical potential, I'm going to associate that I'm in topological trivial phase or topological non-trivial phase. Basically, if if the direction of the precession is along one direction, I am in the topological non-trivial, and if the precession is along the other direction, I am in topologically trivial case. And this also holds not in the equilibrium situation, but when I do quenches, that we see the two different orientations of the precession, and this is going to be abrupt and going to tell me the nature of the transition. And finally, I have new phases that can emerge. I can, for example, in phase 3, I can have two different natures of oscillations. For example, in this case, I have an oscillation that can be with pronounced amplitudes, or I'm going to go to another phase with a smaller amplitude. This doesn't exist in the case of S-wave. But finally, we are able to explore one of the subtle cases in condensed matter systems that are competing orders. So you think about the physics of cuprates. The challenge is that there are very different phases that are very close in energy, and the question is which one wins and which one not, depending of the situation between the pressure, the temperature, when you quench the system. And I mean, these are just some of the examples of very intriguing competing orders that we have in condensed matter systems. We are able to, and there are many open questions about that. The interesting part is that because now we have two order parameters, the P and the D order parameter, I should be able to actually understand what are the intertwined competing orders of these two phases. For example, at equilibrium, if we look at the phase diagram, we can have a situation where the D if the order parameter is stable, we can have also a situation where the P order parameter is stable. So for example, in one case, this can be visualized by one minima stable or the other minimal stable, or even a first order phase transition where I have two minima and one goes from one minima to the other abruptly. So we can, in this case, the two phases can coexist and can switch. And for example, this can be that we are in one minima that is higher in energy, the other is the lower minima, and you can have actually cases where the order is not stable, and if we prepare a phase where the order parameter was zero and the other order parameter is finite, they can revert as a function of time dynamically. So this is the nature of computer orders, when they can switch as a function of time. Or we can try to do, for example, different quenches where, for example, the D order parameter was completely zero. We can make the D order parameter finite, and we can see that in contrast, where the case where the D order parameter was zero, the phases either remain the same, in this case, changes from 3 prime to 3. If the D order parameter was zero, it could be remain always 3 prime, but in this case, it switches from 3 prime to 3, or from 3 or goes from 3 prime to 3 prime, depending of the characteristic of the initial state. So I know this is a little bit complicated, but I think this is super exciting because really opens the possibility to dynamical probe different competing orders in a very simple setting. And with that, I think I am almost done with time. So just hopefully I convince you that there are very rich opportunities by using optical cavities. So I told you today about the quantum simulation of synthetic quantum matter, where we can use spins that are much easy to cool down and emulate phases that has never appeared and have never been seen in solid state materials or even in ultracold atoms. And with that, I hopefully really convinced you that this system is magic. So thank you for your attention.
Thanks for the wonderful talk. So time for questions.
So, I mean, this is a little bit speculative, but let's imagine the following scenario, that you have this egg carton potential and you are putting in atoms in a periodic way. Now let's ionize some atoms from there, okay, and create ions. Okay, so now I'm trying to draw an analogy with the Cooper pairing mechanism. So now you have, of course, the egg carton lattice is a rigid lattice. But now you have peppered this lattice with a few ions. Do you think that you could have, in such a scenario, a phonon-mediated coupling between?
Yes, I mean, I didn't emphasize that, but yes, our first proposal of the P plus IP superconductor was in ions. So yes, is this paper where we show, I mean, in the P plus IP in this case emerges because in the parent trap, the ions are rotating. But exactly yes. So it's exactly the same. So
no, but that is in the penning trap, right?
Yes.
I'm talking about a mixture of atoms in a lattice potential. like, the egg carton potential.
Mhm.
And in that, so I'm not talking about an ion trap anymore.
Ah, okay, okay.
What I'm saying is the following, that if you now ionize, let's say, a pair of ions
Mhm.
from this egg carton potential,
Mhm.
do you think there is a kind of a pairing mechanism that can actually happen because of the presence of the atoms alone,
Mhm.
without the requirement of a overall ion trap?
Yes, I mean, the question is, what is the statistics? I mean, if you are thinking about implementing via an spin mapping artificial, or you want to really look at the pairing?
No, you just want to look at this pairing.
Yes, but I think the point is that, I mean, maybe there is attraction between the particles, but is statistics going to play a role or not? Or because in this type of pairing,
Yes, of course, this is fermionic pairing. Yeah.
exactly.
So
I think we will have to think in what sense there is going, I mean, what is going to be the tendency of the particles, because if they're localized, they're
yeah,
fully.
it would be polarization mediated. If the pairing happens, it's going to be polarization mediated by the path of.
Yes, I will call this will be a Holstein, what people call Holstein model, where you have particles that are localized in some sense, but they are the phonons, they are connecting by the springs.
Okay.
And then you can have, yes, there is some type of pairing, but I don't know if this can be directly mapping to this. But these are the Holstein models, and actually Ignacio Cirac and Eugene Lembler have some ideas on that.
If there are no more questions, we thank Ms. Anna Maria Ray for a wonderful set of 3 Chandrasekhar lectures.
Thank you.